Hello, Algebra 2 students. Welcome to 5.7, Applying the Fundamental Theorem of Algebra. As you can tell today, this lesson is very important. It's fundamental. It's also very fun, obviously, since it's in the title. I know, I tell great jokes. All right, so the Fundamental Theorem of Algebra. It does sound important. It is important. It's not... I don't know if I would call it the fundamental theorem of algebra, but that's what everybody else calls it, so that's what we're going to go with. But before we get into what the fundamental theorem of algebra says, we're going to first look at this little function, and we're going to figure out, well, what are the zeros of this function, and how many zeros are there? Well, luckily, this function is in factored form to begin with. So hopefully you weren't thinking, oh, I got to multiply this thing all out, and then I got to factor it, because that work is already done. It's already factored. Okay, it's in factored form. And we know if we want to find the zeros of something in factored form, we just set each of the factors equal to 0. So we'd set this factor equal to 0 and get x equals 3, -4, and -6. So there are the zeros of this function. Those are the only ones. And it looks like there are 3 of them. Now, we have to sort of make a new definition, sort of. Not necessarily a new definition, but we have to get something out of the way before we move forward. This function could also be written as x minus 3, x plus 4, x plus 4, x plus 6, x plus 6, x plus 6, and x plus 6. Okay, barely fits on the paper. All right, we could write it like that because x plus 4 is being squared. X plus 6 is being raised to the 4th power, so there are 4 of them. And you could set each of these factors equal to 0. All right? And if you set each of them equal to 0, you'd still end up with only these 3 answers, 3, -4, and -6. However, -4 would show up twice, and -6 would show up 4 times. While that doesn't make them any more important, we are going to say that if that's the case, we're going to say that -4 is a repeated solution, or 0 is another word that we say, solution or 0. Okay, and more specifically, it's repeated twice. And -6 is also a repeated solution. /0, and this one's 4 times. So there are only 3 zeros, but technically we could say that there are 3 zeros, but if we count repeated solutions, there's a total of 4, 5, 6, 7. There'd be 7 solutions for this. Even though there's only 3 distinct ones, we are going to say that there are 7 solutions for this. All right, with that said, let's go into what the fundamental theorem of algebra tells us. If you have a polynomial, f of x, and it has a degree of n, remember the degree means when it's multiplied out, it's the largest exponent of the function. So if you have a degree of n, and n is 1, 2, 3, 4, it's anything bigger than 0, then f of x equals 0 has at least one solution in the set of complex numbers. All right, so this function with a degree of 1 or larger has to have at least one 0. Okay, it could not have no zeros. All right, so let me give you a quick example here. X squared plus 2x plus 2. Okay, this function has a degree of 2. 2 is the largest exponent. If I were to find the zeros of this function, I could use quadratic formula. -2 plus or minus the square root of b squared minus 4ac all over 2a. So I get -2 plus or minus square root of -4 all over 2. and x equals -1 plus or minus 2I. Okay, so, just plus or minus I. I'm sorry. So we have -1 plus or minus I. Well, what you'll notice right away is that this solution is imaginary. Okay? Now, that means there are no real solutions to this. But if you look at the fundamental theorem of algebra, it says that it has at least one solution in a set of complex numbers. And complex numbers are both real and imaginary numbers. So keep in mind that this is not pertaining only to real numbers, but it's real and imaginary numbers. And that maybe solutions won't be real, they'll be imaginary, but they're still there. Now, more specifically, the fundamental theorem of algebra says that if you have a polynomial function with a degree of n, then it has exactly n solutions or zeros. Okay? And that's more specific than before. All right, think back to this. This one had a degree of 2, and the fundamental theorem of algebra says that it has to have exactly 2 solutions, or 2 zeros. And you'll notice we had 2. -1 plus I, -1 minus I. 2 solutions there. They're imaginary, but they're definitely solutions. Now, this is only true if each repeated solution is counted as a repeated solution. So, if you have a solution that's repeated twice, it's counted twice. If you have a solution repeated 3 times, it's counted 3 times. If we count those repeated solutions individually, then it guarantees that if f of x has a degree of n, whatever n is, there's going to be n solutions to that polynomial function, or n zeros. All right, so some of the homework problems are going to be just as simple as this. Determine the number of solutions, or zeros, for the following polynomial functions. So I'm not asking you to find the zeros. I'm just asking how many zeros are there going to be. So let's look at the first one. F of x equals 3x cubed plus 2x squared minus 4x plus 1. So the goal is to find out what the degree is. Okay? You must determine the degree of the polynomial, or what is its largest exponent when it's multiplied out. So we look at this one. We look at the degree. The degree is 3. So that means there are going to be 3 solutions. Easy as pie. Okay? So let's move on to the next one. I'm not asking you to find the solutions, just know that there are 3 for that one. Number 2, first thing we have to do is we have to find the degree. Well, it's a little bit trickier when we have things written out like this. Okay? There's 2 ways that you can think of this. This is already in factored form, so you could find the zeros. You have a 0 of 3. You have a 0 of -4. And you have a 0 of 3/2. And you have to think to yourself, well, how many times are each of those repeated? Okay, this one is twice, because it's got the 2. This one is 4 times. And this one is 4 times. So really you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 solutions. Because remember, we're counting the repeated ones however many times they're repeated. So another way to think of this one is if you were to multiply this out, and I don't want you to because it's a lot of work and it's unnecessary work, but if you were to multiply this out, when you multiply this one out, you get an x squared as the highest term. When you multiply this one out, you get an x to the 4th to the highest term. Same thing with this one, you get an x to the 4th to the highest term. Well, then when you multiply all these together, x squared times x to the 4th times x to the 4th, you get x to the 10th. So if you were to multiply the whole thing out, the highest term would be x to the 10th power. And as we know, that's the degree, so that tells us how many solutions there are going to be. So we get 10 solutions. Either way you want to think about it. All right, let's try the next one. Next one is probably the trickiest one. You have to figure out how many solutions there are to that. All right. So, well, if I multiplied this out, x squared minus 4x plus 1 to the 3rd power, I'd have to do x squared times itself 3 times because it's to the 3rd power. So x squared times x squared times x squared. That would give me an x to the 6th. And if I multiply this one out, that would give me an x squared. X to the 6th, x squared. And then if I multiply those two together, I would get an x to the 8th. So if x to the 8th is the largest exponent, that guarantees that there are going to be 8 solutions. All right, so sometimes you have to look a little into it and say, well, all right, what would the largest exponent be if I multiplied everything out? All right, so let's go to our next one. It says, find all complex zeros of the following function. Now notice the directions are a little bit different here. Before you were doing problems that said, find all real zeros of the following function. Well, now we're dealing with complex zeros. Complex zeros are a little bit different just for the fact that complex zeros are both real zeros and imaginary zeros. So not only are we looking for the real answers, but we're looking for the imaginary ones as well. So keep that in mind when you're doing these problems, because sometimes you're looking for both real and imaginary. So the first thing we always want to do is graph it to see if we can find any solutions that are easy for us. Okay, ones that we don't have to do a whole lot of work for. All right. So let's graph it. I've got a bad window range. Holy smokes. Let's just go zoom standard to my normal window range. All right, so that's what it looks like. I can't see the whole thing, but I can see enough. I can see a couple of zeros. If I trace it, I'll confirm. It looks like there's one at -2. Yep, sure enough. And it looks like maybe at 1. Yep, it happens at 1 as well. Now that's an interesting one. Usually we don't see zeros like that. That one just comes down and just touches there at 1 and then goes back up. But it does touch there. So we're going to take those zeros that we just found on the calculator. -2 and 1. And we're going to sort of use them to help reduce this. We know that if -2 is a factor of 0, that x plus 2 is a factor. And if 1 is a 0, then x minus 1 is a factor. So these are factors. So what I'm going to do is I'm going to divide them out of my original equation. And when I divide them out of my original equation, I'll have a smaller function left over to deal with. And hopefully I'll be able to find the zeros of that function. These are 2 zeros. We know that there are 5 because 5 is the largest exponent. So we have to find 3 more. So what I'm going to do is I'm going to take -2 and factor out x plus 2. 1, -2. I'm going to use a 0 for the x cubed term because there's no x cubed. 1, -2, -4, 8, 8, -16, -8, 16, 3, -6. Okay, sure enough, we get a remainder of 0. If you didn't, you know you did something wrong. And then I'm going to factor out x minus 1. So I'm just going to continue with this by putting 1 up there in the corner. And we get 0 as a remainder for there as well. So what we're left with for f of x here is we're left with x plus 2, x minus 1. Those are the 2 things that we factored out. And then what we have left here, which is x cubed minus 3x squared plus 5x minus 3. And so now we have to find the zeros of what we have left over in here, x cubed minus 3x plus 5x minus 3. Well, this one we could try factoring by grouping because it's a cubic, but unfortunately factoring by grouping does not work. So really the only other way that we have right now is to just maybe try and graph this. And if maybe we'll find another solution when we graph that one. So we're going to do that. We're going to go back to our graph, back to the y equals. I'm going to just turn that one off and then graph a new one here down at the bottom. X to the 3rd minus 3x squared plus 5x minus 3. And take a look at that graph. Okay, it looks like maybe 1 again. Yeah, definitely 1 again. So this one has a 0 at 1 as well. Well, what that tells me, because before, remember, we already have a 0 of 1. and we factored it out here, but this thing also has a 0 of 1, which what that tells me is that 1 must be repeated more than once. So it looks like we have a repeated solution. So what we can do is we can also factor out that next x minus 1 factor. Okay, so that means another factor is x minus 1, so it's a factor twice. And so if I factor out a 1 again from what I have left over, 1, negative 3, 5, and negative 3, hopefully I get a remainder of 0. Absolutely. So f of x has now been reduced to x plus 2, x minus 1 squared, because there were two factors of x minus 1, and now x squared minus 2x plus 3. All right, we finally reduced it down to a quadratic. And in this quadratic, we have so many ways to solve quadratics. We'd spend an entire chapter on solving quadratics. So we can just take this x squared minus 2x plus 3 and set it equal to 0 and solve it. So I'm going to use quadratic formula again. 2 plus or minus the square root of b squared minus 4ac all over 2a. Oh, and a is 1. So all over 2. And I get 2 plus or minus square root of negative 8 all over 2. And that does reduce. X equals 2 plus or minus 2i square root of 2 over 2. All of those are divisible by 2. X equals 1 plus or minus I square root 2. And so our solutions, all 5 of them, are x equals negative 2, 1, I'm going to put a little note here, repeated twice, 1 plus I square root 2, and 1 minus I square root 2. So there are 1, 2, 3, 4, 5 solutions, just like we thought there was going to be. Some of them were a little ugly, imaginary, but that's okay. But we do get 5 solutions. Now, one thing that I want to comment on is the original graph that we looked at. You can actually tell from the original graph whether or not a solution may or may not be repeated. So we had one at negative 2, and if you remember, the solution at negative 2 was not repeated. But we also had one at positive 1, and that one was repeated. If you get a graph that comes and just sort of touches the x-axis and then goes back up, or from the other direction, if it just goes and touches it, that guarantees that it will be a repeated solution. So looking at this one, since it just touches there, we could have known right away that 1 was going to be a repeated solution. And so maybe we didn't have to regraph the second graph that we did. We could have just factored out 1 twice. So that's an option for you, and if you can recognize that, more power to you, and it'll save you some time. All right. I think we're going to make 2 separate videos for this. All right, so this is going to be the end of the first video, but there will be another video. So hopefully we did 1 video in class and you do 1 video at home. If not, I apologize, you got a lot of videos to watch tonight. But regardless, I hope you have a fantastic evening, and hopefully this is making a lot of sense to you. Have a great night.